Hello everyone. Today we're going to work on a coupled pendulum. It consists of two pendulums connected by a spring. First, I'll add a revolute joint to represent this pivot. And for this mass, I'll use a spherical solid. I'll rotate this frame by 90 degrees about the x-axis. In this transformation block, select cylindrical. This will shift the coordinate about the pivot to define the pendulum length. In this video, I'll use these parameters, and I'll set the variables in the model workspace. Alright. This block defines 0 at the right side of the pivot. If I use positive 90, the mass will be placed at the top, so using negative 90 places it here. And I'm going to set this radius to 0.2. Then define it as a point mass. Now we have one pendulum here. So I'm just going to copy this system and connect it here, and then shift it by D. And for this spring, it attaches directly to the mass. So I'll place it here, after the transformation block. If I connect it before this block, the spring will attach at the pivot, which is not what we want. And I'll set the natural length to match the distance between the joints. Then I'll measure their angles to observe the motion. Okay, now let's set the initial angle for this pendulum. Let's use pi over 30. Here we go. As you can see, it works. Each pendulum oscillates about its joint. Now, let's take a look at the time responses. This looks okay. This one starts from its initial condition. Looks good. Now let's add the excitation to this joint and see how the system behaves. Okay, then I'll excite it with a harmonic. I'll turn off the initial condition. Let's see. I think it would be better to verify the responses with the mathematical model. In this case, I'm going to use the linearized equations of motion. And I'll build this model using a state space block. We can rewrite these equations in state space form like this. So I'm going to put this matrix into this block. For the input matrix, we only want to excite the first pendulum. But for the output, we want both of them, so it should look like this. And I'll leave the initial conditions to 0. Since we measure both angles, the output will be in vector form. So we have to split it to view each response separately. Theta 1 will go here, and theta 2 will go here. Alright, let's see the results. As you can see, the results match well. The difference you see here just comes from the difference between the nonlinear and linear models. Now, let's take a look at the system's mode shapes. These are the natural frequencies and mode shapes of this system. For the first mode, you'll see in-phase motion. The pendulums move together, like this. But if you look at the time response, you'll see a large difference between the physical model and the linear model. This is because when the system is excited at resonance, the motion becomes large, and the linearized model does not work well for large angles. For the second mode, you'll see out-of-phase motion. The pendulums move in opposite directions, like this. As you can see, they're completely out of phase. And you're going to see the difference between these two models in the time responses. And if you use the mode shape as the initial condition, you'll see pure mode motion. In this case, I'll use the second mode. In the state space block, you have to enter it here. Let's see. As you can see, the pendulums remain out of phase, and if you look at the time responses, you'll see they oscillate at a single frequency, which is the second natural frequency. And this clearly shows the difference between these responses building up over time. I hope you found this helpful. If you have any questions or want to see a specific topic, let me know in the comments. Thanks for watching, and I'll see you in the next video.